Hi there and welcome. I'm Matthias Peyer, professor at EPFL and leading the HexHive research group. I will try to present you an overview of what kind of research we are doing in my research group and what kind of interesting topics we are trying to tackle. And additionally, I'm trying to convince you to come to EPFL to do your PhD. At the HexHive research group, we focus predominantly on software and system security. And we are facing several challenges in how we can protect systems against the exploitation of vulnerabilities and different kind of issues. We are facing several challenges in this regard. One of the main challenges that you're likely aware of is that there's vulnerabilities everywhere. There's all these classic systems such as your desktop systems, your cloud, your smartphone that are vulnerable to a large amount of issues and have to constantly be patched. Otherwise, adversaries will be able to take over your systems. But it doesn't just stop at desktop systems or regular computing systems, but more and more we have small scale devices and IoT systems that can be taken over. And these start to introduce and intrude into our private lives. For example, an attacker could take over your smart lock, your smart camera, or even turn your smart car into a remotely controlled toy vehicle. While this may be fun for the attacker, it's not as much fun for you if you're sitting in a remotely controlled car. Now, as you see here, there's vastly different computing systems that have to be checked and controlled, and there's a large amount of threat surface that we are trying to protect on very, very different systems. This makes this interesting, but also challenges for us to design different approaches to protect these kind of systems. The second challenge we are facing is software complexity. Since many years, software has only gotten more complex. While it has only taken us a couple of meters of complexity to fly to the moon if you print out the source code of the system, if you look at the Google Chrome source space and a Linux kernel, we have more than 100 million lines of libraries, runtime environments, compilers, approximation, kernel, and so on, to just look at cat pictures in the case of Google Chrome. If you print all of this and stack it on top of each other, you end up with a stack of 370 meters of complexity, which is a massive amount of complexity. And we need to design tools that are able to cope with this amount of complexity and can find vulnerabilities in them and can protect these kind of systems. Now, in my group, we focus on two different aspects to protect and to address these challenges. And these are testing and mitigation. And I will try to give you an intuition of where these two different parts are being used. Software testing is what you do ahead of time before software is actually being deployed at a customer or at a user. And software testing predominantly discovers bugs. So it is a development tool that is result-oriented. Any bug that you find and fix during development will no longer be exposed and cannot be used by an attacker to compromise your system. There's resource costs, and developer resources are likely limited, so we will never be able to find and fix all the vulnerabilities that are in there in the source code. That's why we have to develop mitigations alongside. And mitigations are like small changes that are introduced by the compiler or by the runtime system or by the hardware that make exploitation of a remaining vulnerability harder. As there will always be remaining vulnerabilities, these mitigations are always on and try to detect some form of exploit condition or vulnerability condition at very low overhead and stop the exploitation at that point in time. Let me give you a little bit more concrete example of what we are looking at. We are looking at low-level system code, as in C or C++. And in software testing, we would look at two different aspects. For example, we would try to create policies that allow us to detect vulnerability conditions. For example, we can replace unsafe functions with functions that do additional checks that come at a higher runtime cost, but allow us to detect violations of, for example, memory safety policies. These kind of instrumentation modify the program during compilation. They add quite a bit of overhead, but they allow us to detect whenever something goes wrong. Or secondly, we're trying to do some form of automatic test generation. For example, this vulnerable function that is in here can be executed with a large amount of different strings. And we're trying to define techniques that allow us to create different kind of test inputs along certain conditions or along certain variables and environments, allowing us to actually trigger different kind of odd behaviors in the programs, so that developers can use these traces and information from the vulnerabilities that we find to then find and fix the underlying vulnerabilities. Or secondly, for mitigations, which are also instrumentations but are much more lightweight. So for example, we can insert a check at this point in time before the function pointer is actually being used, so that to make sure that the function pointer actually targets a benign function pointer that is in the set of allowed targets according to some kind of security policy. And this allows us to protect against certain kind of attacks, but not against all of them, because the mitigations have to be low overhead. In a larger project that we're working on, we're trying to combine the results from software testing and mitigation, try to combine the benefits of both. So we do have source code that is written in a low-level language like C or C++. We compile it using our newly developed policy-based sanitization. We are developing different kind of policies here, depending on what kind of properties we are looking for. For example, memory safety, type safety, data race freedom, or other kind of common errors that we're trying to protect against. We analyzed the overall system, trying to infer and complement the policies along it, and will produce an executable with the necessary debug information. We then have a set of tests that the developer likely wrote, and we'll use these tests to run our debug executable. We may be lucky and already find some vulnerabilities or bugs. We'll report those to the developer and allow them to fix them in this and update the source code, where we then rerun the analysis. In a second step, we'll do, based on these existing tests and on coverage on which parts of the program have already executed, we are developing different forms of test inference mechanisms or fuzzing approaches that allow us to reach other parts of the program and automatically generate different kind of test inputs that allow us to have a good overview of what areas we cover in the program and what kind of issues are remaining. So the combination of policy-based sanitization and automatic test inference gives us a good intuition on which parts of the code we actually cover, what policies we can enforce, and how these different things tie together. Based on the information on what we have covered, what we have tested, we are then developing customized mitigations that allow us to protect in a custom tailored way against any of the remaining issues that are left in the code. So we cover pretty much everything from compiler-based analysis for security policies to automatic test inference, mitigation of remaining vulnerabilities at very different levels of abstraction. So that it could be implemented as a binary analysis or as a compiler-based defense. And we are working at both ends, or all the different ends of abstraction. Now, you may be asking yourself, why should you join the Hive? In the HexHive at EPFL, we have a very dynamic research group of a large set of enthusiastic PhD students. We are all working together. We are meeting at least weekly. There's one student presenting their research project. We have several focused research meetings for 2 or 3 people where we discuss their individual research results. We hang out and then go to conferences like the Case Communication Congress, where we play as CTF teams. We meet for social events, and as you see at the bottom right, we're actually hanging out socially even during the Corona crisis to discuss common events and things that are happening during the day, even in a virtual environment if needed, allowing us to exchange information and keep in contact. It's a lively group with different students that are all working together in similar but related projects and pushing towards this common goal. So why should you come to EPFL and work on software security? Well, for me, the software security aspects is, or one of the main aspects here is that it crosses all the different abstraction layers. So we can work at low level ISA abstractions up to the web. If you look at the Google Chrome browser, you combine security mechanisms from the lowest level of the underlying ISA that you're executing on up to the highest level of where you're interpreting data from the internet and displaying it as cat pictures on the GPU. So this is extremely diverse and extremely interesting to look at all these layers of abstractions. Mitigations protect the systems against different forms of attacks, and in software testing, we find and fix these vulnerabilities. And the security mindset is that we are trying to understand, think outside of the box, analyze these complex systems, and then develop processes and analysis that allow us to find bugs and mitigate negative effects. All the research that we do in my group is open source. You can find more information about recent projects on our group homepage, which is hexhive.epfl.ch. And ping us if you have any further questions. We are on Twitter. We are reachable on Facebook. And I would be happy to hear any follow-ups from your end. So let us know if you have questions. Otherwise, I would thank you for your attention.